After defining several geometric properties of vectors, like length, angles, and so on, now we would like to provide some geometric operations we can do with them. For example, we would like to project vectors onto subspaces. We define a projection as a linear mapping that takes a vector in V, a generic vector space, and outputs a vector that stays on a subspace of V. Also, this particular linear mapping has the condition that if we apply 2 times the linear map to a vectors, the result should be the same as apply this function once. Here, in fact, we see that pi of pi x should be equal to pi x. If these conditions are met, then pi is a projection. But why we give this definition to a linear map and say that if pi to the square to the power of 2 is equal to pi, then this function is a projection? Well, because the projected vector can't be projected anymore and go elsewhere. So everything that goes in U, in the subspace, should stay in U when we project it again. And here we can see several pictures that provide several definitions of projections. But if we take, for example, this projection, this perspective projection, the square, the cube is projected onto this plane. But if we take this projection and project it again, we obtain again an element on the subspace, and it's the same. That's what a projection does and can be characterized. Remember also that we can represent a linear map using matrices. Here, for a generic linear map, this is a slide from the course, the first course. We have seen that a phi linear map can be represented with a transformation matrix that, if multiplied by a vector of coefficients, gives the coefficients of the transformed vector that stays in the W vector space. So the transformation matrix can map coordinates with respect to the basis of V to coordinates with respect to the basis of W. We can do the same now with this particular linear map, which is the projection. So this transformation matrix is said to be P pi and can be used to express the condition that lies onto the projection function. So the square of this matrix must be equal to the matrix itself. Now we will stop talking about projection for a minute, and we will focus on what an orthogonal complement is. So consider a generic vector space V that is m-dimensional. So it has the basis as m vectors. And we take U as a k-dimensional vector subspace of V. Now we say that given V and U, the orthogonal complement of U is a m minus k dimensional vector subspace, and it is defined in the following way. So every vector that lies on the orthogonal complement of U is orthogonal. Here we express the orthogonality using inner product to each of the vectors that lie on the subspace U. So everything that we consider V our macro vector space. We take U, a particular subspace, and every vector that is perpendicular, that is orthogonal to U, lies on the orthogonal complement of U. For example, in R3, we can take this a line as a subspace. So we take the real numbers, one axis, and X lies on this axis. The orthogonal complement, so, is defined as the plane on which every point of this line is perpendicular to. Defining orthogonal complement, we can also prove one fundamental property. Every vector in our general vector space can in fact be expressed as the sum of two vectors. One of these lies onto our defined subspace and the other on the orthogonal complement of that subspace. In fact, since U and the orthogonal complement of U equals to the null element, because both are subspaces, then V can be expressed by k vectors of the basis. The term lies on in the subspace U, and m minus k elements onto that lies on the W, which is our orthogonal complement. The orthogonal complement is very important, and it's as you can already understand, it relates to the projection concept. For example, let's take this picture and examine this projection. So don't worry about the term projection, but let's say that A is projected onto this subspace in which B lies on it. B is in our subspace. How can we express this generic vector A that lies on V? Well, it can be expressed with a vector A1 that stays in U and another vector A2 that is perpendicular, orthogonal to our subspace. Now, we have defined what is a projection. We have defined what is an orthogonal complement. We can put this concept together and get the orthogonal projection. So, let's take V as an inner product space. Let's define pi of U as a projection. Here we explicit the subspace U. If x minus the projection of x computed to U, which is every vector in our subspace, and the inner product of these two vectors equals to 0, then this projection is said to be orthogonal projection. As in the graph here, we can see that x minus pi of x is the vector that goes from pi of x to x. Here, this is the vector. In a generic projection, this vector could be everything, could have whatever angle to U. In orthogonal projection, since this condition lie, it means that this vector, here the first term, should be orthogonal to U, which is a generic vector in the subspace. Also, we can see that thanks to the orthogonality condition, pi of x is the closest vector in U to x. Why? Because this is minimal when equal to 0. Now we would like to compute the projection matrix that fully characterize the projection on a Euclidean vector space, considering the inner product space in which our inner product will be the dot product. First of all, let's express pi of x as a linear combination of the bases. Which basis? Well, the k vectors of the basis where these vectors lie on U. This linear combination can be expressed, as we already done a lot of time, as the multiplication between the matrix of the basis and the lambda, which is a vector of coefficients. Here you can see is a matrix where every column of this matrix is a vector of the basis. So, to fully characterize our projection matrix, what we want to determine are the lambdas, this lambda vector. To determine this lambda, we will start by the definition of the orthogonal projection, which is a projection that satisfies this condition. So, here, instead of taking every vector on U, we take the vector basis. We express the inner product as the dot product, and again we can express pi of x as the multiplication between the matrix, the basis matrix, between to the lambda vectors. What we find here is an homogeneous linear equation system. Remember that we say that the linear equation system is homogeneous when the term on the right is equal to 0. So this system can be easily solved if we express, as we already done multiple times, this system with the matrices. Here we have that this equation is expressed for all I equal to 1 to k. So let's take again, we can define the matrix B here. This synthesizes the system that is expressed through this I, with I equal to 1 and k, to k. Now, given this expression, we can compute the subtraction and get that this matrix, which is an invertible squared matrix, times the lambda vector is equal to B transpose times x, the vector we want to project to U. Since this is an invertible squared matrix, then we can take the inverse of this matrix and finally get and express the lambda vectors, the lambda vector. So with this expression we are able to compute every lambda coefficient that determines, remember here, that determines our projection vector, orthogonal projection vector. So for every vector x, we are able to compute the coefficients that are uniquely determined and uniquely determine the projection through the linear combination. So lambda is this. Remember that pi of x is b times lambda, and here we have lambda and this is b. But what is pi of x expressed to the projection matrix? Well, is projection matrix times x. So here we simply delete the x vector and we can express the projection matrix. Let's take a look if u is a line, an axis. What we get? We get that b, the vector, the basis, is an m times 1 matrix. So the b transpose times b is a number. Why? Because b transpose is a 1 times m matrix and b is a m times 1 matrix. In the dot product we delete the inner dimensions, so we get 1 times 1. Of course we take the inverse, which is 1, which is the fraction of that number. So we can write that the projection matrix, when u is a line, is an axis, as b transpose times b transpose divided by b transpose times b. This is a number, while this is an m times m matrix. Remember, because this b is m times 1. B transpose is 1 times n, so the inner dimension is deleted in a multiplication between matrices, so we get m times m. In particular, what we get here, remembering how we defined B, is this matrix. What we get here instead, on the green term, well, is a normalization term. Is the sum of the squared of the coefficient. So it's the squared of the norm. We are normalizing this matrix. Once we have defined our projection matrix, we can also take a look to the projection function, the orthogonal projection, which is defined as lambda times b, which is equal to this one, the inner product between x and b divided by the square of the vector b. We express the inner product as the dot product, and finally we can get that the norm, the length of the projection of the projected vector, is equal to the absolute value of lambda times the norm of the basis. Again, here we can see that expressing this term we get through the definition of cosine that the norm of the projected vector is equal to the absolute value of the cosine of the angle between b and x times the length of x, the length of b, and this term. This multiplication equals to 1, so we get that the length of the projected vector is equal to the absolute value of the cosine of the angle between the two vectors and the length of x. So if we project A in this picture, A in this expression is equal to x. So pi of A is equal to the cosine theta here of theta times the length of A. We get the definition, finally the usual definition of projection. So this is A1. So A1 is of course the cosine of theta applied to the length of A. Here we have some more examples. For example, here we have the projection of x onto the subspace U defined with this basis vector B. And here we have for a vector x which is a unit vector, we have the expression that the projected vector is the cosine, because the length of x is equal to 1, and the orthogonal vector to the projection, to the vector that stays on the orthogonal complement of our subspace is sine of the angle. Last example, here we see that several points, several vectors projected onto a linear subspace, an axis. The last section will treat instead how to rotate vectors. Previously in this section we have seen how to project vectors. Now we want to understand how to rotate them